Now we want to talk about gravitational forces. And I simply give you Newton's law of universal gravitation. Okay, Newton's law of universal gravitation says that if you have mass m1 and mass m2 separated by some distance r12, okay, then the magnitude of the force of attraction in gravity only exerts attractive forces, forces of attraction. Unlike, let's say, electrostatic forces, forces between charges, they can be attractive or repulsive depending whether you have like or unlike charges. Okay? Gravitational forces are always forces of attraction. So you have a force of attraction of this magnitude. Now there are no arrows on anything here, so we're just talking about magnitudes. So to get the gravitational force between two masses, you multiply the masses and divide by the square of the distance between them, called an inverse square law. Very important to understand that and what it means. Now the big G is just a universal constant that we can measure in the lab with lead balls or other masses. Now it's very tricky to measure it with any accuracy, but we refined our experimental techniques. We could measure it in our lab if we could turn the air conditioning off, but we can't do that. So the circulating air currents, the forces are very tiny. The forces we can get between two lead balls in the lab are very, very tiny, and circulating air on the lead balls messes everything up, so it won't work. But in any case, big G is something we've measured with, or something experimentalists have measured with great precision, with really good precision at least. So we know the value of G to several significant figures. Okay, this also makes sense. If I have a mass here and a mass here, okay, they're going to exert a certain force of attraction. Now, if I take this mass and another one just like it and lump them into a bigger mass, okay, so now I've got a bigger mass here, twice as great as the first one. Well, this mass here is attracting each of the two masses with the same force, so the force is going to be twice as great. Also, the force exerted on this mass by these masses is going to be twice as great because now you have two masses here that this thing's going to interact with. It's going to interact with each one separately. So if it interacts with just the first one, it's going to have whatever that force is. If it interacts with the second one, it's going to have an equal force. So if the two masses here are melded together, then we're going to have twice the force of attraction between this mass and this now doubled mass, as opposed to the original masses. Okay. And that's how you get, it doesn't prove anything. Experiment is the only thing that proves anything, but that's a plausibility argument. If one of the masses gets bigger, twice as big, then you're going to get twice the force. And if one of the masses got 14.8 times as big without changing the other, you'd have 14.8 times the force. The other part of that is your distance, and you can simply think of the gravitational influence of, let's say, this mass as being spread over a sphere at any given distance. So if I want to get the influence of this gravitational force here at this distance, I look at the sphere and imagine the gravitational influence of that mass spread over the surface of this sphere. Now, if I want to take this and look at a greater distance, I've got to spread the mass over a bigger sphere. And if the sphere doubles in radius, what happens? Its surface area, the area over which the gravitational influence is spread, gets 4 times as great, because the surface area of a sphere is proportional to the square of the radius of the sphere. So it makes sense to have an r squared down here. Just makes intuitive sense. It fits with our intuition. An experiment validates this with great accuracy. Up to 1 part in tens, hundreds of thousands. I don't remember exactly how many significant figures we do know the gravitational constant to, but quite a few. Okay, so that's the idea of the gravitational force. And also the gravitational force acts along the line joining the two masses. So this mass is attracted right to that one, that mass is attracted to this one. I've also been a little bit careless with my terminology. These really need to be particles and not extended masses, but let's just assume that they're spherical, homogeneous objects and act then like particles for reasons that you can explain using your multivariable calculus and prove, but we don't want to go there. So you can read more rigorous accounts, read what your textbook says, but I've tried to give you the intuitive flavor of this thing. Okay. Now, there's a vector expression for the force. So we get the force and distance in one calculation, and the force and its direction in one calculation. And I'll come back to that in the next clip.